forces. This is actually for my grade 10 students. So if I have a student here with mass M1, let's say, 55 kilograms, and then another student, M2, let's say 60 kilogram, sitting a distance of 1 meter apart, or let's say D, some call it, some use R. So what is the force of attraction between these two students? So the force of attraction, so they are going to be attractive forces, but you're going to see this is the force that 2 applies on 1, and this is the force, action-reaction, the force that 1 applies on 2, and they have the same magnitude. So the gravitational formula for the force is going to be G. G is a constant. This is the gravitational constant. M1, M2. So what am I doing here? I'm taking G, multiplying it by M1, multiplying it by M2, and then dividing it by the distance between the two masses squared. Okay, so this is the magnitude of F. You see how F is inversely proportional to the square of D. So the farther the students will be, the less force they will feel. Okay, and the force, we're going to see that the gravitational force actually between two students or between two masses of the scale we know is not going to be that big. So in this example here, G, okay, I didn't give you G, the value of G is 6.67 times 10 to the power negative 11. Do you guys know what's the meaning of 10 to the power negative 11? So it is G equals 0, and then I'm going to need to write 10 zeros. So these are 3, another 3, so 6. Another 3, 9, and another 0, and then 6, 6, 7. So tell me, guys, is this constant huge or very tiny? Those of you who said tiny are correct. I could hear you say, oh my God, making fun of the physics teacher. I get that, no problem. So F here is 6.67 times M1, 55 kilograms, times M2, which is, I'm not just gonna put 55, 60, and then 1, okay, what am I forgetting here? Did you catch the mistake? I forgot the 10 to the negative 11, and that is of crucial importance. That's the whole story is there, 10 to the negative 11, and then times 55 times 60 and over 1 squared. If I recall well, we calculated the other day with students, and it was 2.2 10 to the power minus 7 what? Newton, otherwise Newton is going to be very angry. So that is a force 0 point, how many zeros? 1, 2, 3, 1, 2, 3, and then 2, 2. Is this a force that students are going to feel? This is a very, 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 very tiny force. If I want to calculate the force that Earth is exerting on M1, then it's going to be F Earth on M1. I'm not going to calculate that, just approximately it's going to be around 500 newtons. And the force on M2 is going to be around 600 newtons. So what does that mean? It means that, okay, if you are on a cliff and then if you fall, you're really gonna feel how Earth is attracting you. However, if you're sitting next to your classmate, I am not going to see your head going to the head of the other student, unless of course you just wanna, you're bored and you wanna attract attention. That's it. So this is it. Let's see. Then I heard you say, what's the relationship with the 9.8? Okay, so I'm gonna show you. I'm gonna show you that. Okay, so the principle, you know, when he saw that I was posting videos about reviews to my students. He said, you could do flipped classrooms. And I was like, yes, I'm going to do that. So this is planet Earth, our beautiful planet Earth. And this is one of the students here. So we're going to consider the center of the Earth to the student. What's that distance? This is the radius of the Earth. This is the radius of the Earth. So you guys, as a task for you, you're going to go and Google, or you're going to go on the computer or in your physics book and find what is the mass of the Earth. What is the value for that? It's not going to be 55 kilograms. It's definitely not going to be 60 kilograms. That I can assure you. And also look up the radius of the Earth. What is the radius of the Earth? You're going to find it in kilometer. But in physics, we use the SI units. So you're going to have to convert RE. You need to convert it from kilometer to what? To meter. Okay, King Henry doesn't usually like chocolate milk. You know, kilo batata, it's kilogram batata, it means 1000 gram. Kilo anything, it means 1000 of that thing. So kilometer means 1000 meters. So you're gonna find the RE in kilometers. You're gonna convert the RE to meters. You're gonna square that and then put it in the denominator. So F, the gravitational G, is going to be the G, but now it is not Saif and Muhammad Saif, or it's not Ali and Muhammad who are 55 kilograms, 60 kilograms, sitting 1 meter apart. It is one of you guys here on the surface of the Earth. So the first mass is going to be the mighty mass of Earth times the mass of the student divided by the radius of the Earth in meters, not in kilometers squared. And you are going to find the force that Earth exerts on you. And that is also the force that you exert on Earth. But because you're so tiny compared to the Earth, you're not going to see the Earth move towards you. And so this G times ME over RE squared, this is going to be your homework, and I'm going to ask you tomorrow, inshallah, when I see you. This is going to be approximately 9.8 meter per second squared. This is going to be the G that we use as F equals mg. So you see now where this G comes from. It is the gravitational constant G times the mass of Earth divided by RE squared. So this is what we're gonna do tomorrow. So this is part of your flipped lesson. I am going to see whether you got ME or not, whether you got RE or not, whether you converted RE from kilometer to meters, and whether you calculated G times ME over RE squared times your mass here, the mass of student. Every student should have, it's going to be very similar unless your mass is very, very, very big. So it's going to be 500 newtons, 600 newtons, 700 newtons. And then as a task, you're gonna calculate G times ME over RE squared. Please do not forget to convert RE into meters, and then you're gonna find that G. And then you're gonna say, wow, so this is it. Well, at least I'm hoping for that moment or eureka moment. So this is it for the gravitational forces. I'm just gonna talk a little bit of Coulomb forces or the electric forces, and then I'm gonna call it a day, okay? So if you have a charge here, sitting here, a charge either positive or negative, let's call it Q1. Q1, I'm not gonna, it must have a mass M1, okay? And then I'm gonna call another charge Q2, okay? And then it also has a mass M2. And then I have a distance between these two, that is D. So can you tell me what the expression of the gravitational force between these two masses? F gravitational from 2 on 1. And then this guy here is F gravitational from 1 on 2, okay? So Fg, what is Fg? You're absolutely right, G times M1 times M2 divided by the distance squared, okay? Now, the electric force or the Coulomb force is going to have a very similar formula, a very similar expression. So F electric, instead of having this constant G, we're going to have another constant that is called K, or the Coulomb constant. And then instead of having M1 and M2, I'm going to have two charges here, Q1, Q2, divided by D squared. Just like the mass is expressed in kilogram and the distance is expressed in meter, Q1 and Q2, because they are charges, they are going to be expressed in Coulomb, after a physicist called Coulomb. The Coulomb is huge. You know, we are not going to see 2 coulombs or 3 coulombs running around. You are rather going to deal with millicoulombs, microcoulombs, etc. Okay, so microcoulombs, so nanocoulombs, yeah, that works for me too, okay? But what I want to attract your attention to, what was the value of G? And then I was like, oh, you've got 10 zeros before the 6, yes? The value of G was 6.67, 10 to the power minus 11. And the unit, that's another story. I want you to find out the unit for me. So 0.000000, you're saying stop, 0, 0, 0, so 6, 9, 10, and 6, 6, 7. So that's the value of G. You see 10 to the power negative 11. And contrast to that, K is going to be 9. Okay, so it's not 6, it's 9. But times 10 to the power of 9. What? You see, is it negative exponent or a positive exponent? It's a positive exponent. So how many zeros here? 9 zeros. 1, 2, 3, 1, 2, 3, 1, 2, 3. So this is what? This is 9 kilo, 9 mega, 9, this is 9 billions. So what do you feel, or what do you think about G and K? G and K, because when you take your E assessment, you are going to be asked, I really don't care about this. I'm really fascinated by how the electric force usually is way, way, way stronger than the gravitational force. You have seen that a force between two students, 55 kilos and 60 kilos, is 2 times 10 to the power negative 7 newtons. Put some charge on each student and you will see that the electric force is much, much mightier and much, much bigger. So G is 6.67 10 to the power negative 11, while K is 9 10 to the power of 9. And so G is really, really, really negligible compared to K, and that's why when you now, if I invite you, see, let's do a calculation where you've got M1 equals 1 kilogram and M2 equals 1 kilogram, and Q1 equals 1 coulomb and Q2 equals 1 coulomb, and the distance between them is 1 meter, just to see the order of magnitude and to see how much the electric force will, so as to compare the gravitational force and the electric force. So we said M1, M1 equals M2 equals 1 kilogram, D equals 1 meter, Q1 equals Q2 equals plus 1 coulomb. If it is plus 1 Coulomb, are these charges going to repel each other, or are they going to attract each other? Positive charges repel each other. A negative charge would also repel a negative charge, but if you've got a positive charge and a negative charge, they will attract each other. Okay, so let's go ahead and do the calculation. And so I want you to really see what I'm talking about here. So Fg, in the case of 1 kilo, so it's going to be 6.67, 10 to the power minus 11 times 1 over 1 squared, which is 1. So this is going to be 6.67, 10 to the power negative 11 Newton. That's nothing, that's 0. I could really safely say that this is 0. I mean, are you going to feel any force like that? This is really, really, really small. And then F electric, let's say, is going to be 9, 10 to the power of 9 times 1 Coulomb times 1 Coulomb over 1 squared. This is going to be 9, 10 to the power of 9 Newton. Isn't this scary? So it's like I'm gonna have to go all the way from the board, okay? So this is the force, the electric force, okay, all the way, okay? I just need to represent them equal, but you've got the idea. The gravitational force is really meaningless in front of this Coulomb force. Okay, so, and I'm gonna test you on whatever I said today, so be ready, okay? But usually I told you, you're not gonna find any coulombs running around, but even if you put a millicoulomb here and a millicoulomb here, so let's say 10 to the power negative 3 times 10 to the power negative 3. If you're good in math, this is going to give me 10 to the power negative 6, but still with the 10 to the power 9, it's going to give me 10 to the power of 3, and that is 9 kilonewton. Just if you, in the case, you've got millicoulomb here and millicoulomb here. So it's still, you know, like Fe in the case of the charges Q1 equals Q2 equals 1 millicoulomb. So milli is 10 to the power negative 3, 9, 10 to the power of 9 times 10 to the negative 3 times 10 to the negative 3 divided by 1 squared. And this is going to give me 9,000 Newton. If you compare this to 6.67 10 to the power negative 11, this is, you see how this is completely meaningless and negligible in front of the 9,000. Okay, let's try it with microcoulomb now. Okay, so even with microcoulomb, so let's say Q1 equals Q2 equals 1. So, you know, micro, this is the sign of micro. It's a Greek letter, microcoulomb, and the micro is 10 to the negative 6. So you've got here 10 to the negative 6 times 10 to the negative 6, that is 10 to the negative 12 with 10 to the 9, so it's going to still give you 0.009 Newton, which is way bigger than 0.000000. I know you are telling me, okay, miss, we got it, but still I'm just making sure. So even if you consider microcoulomb, you are going to get a much bigger force than the gravitational force. So you've got it. Which force is mightier, electric force or gravitational force? Electric force, okay? And then we're gonna say that electric and magnetic, electromagnetic, we're gonna unify them because they are of the same nature. And we also talked about the strong nuclear that explains how a nucleus is holding together despite the fact that all the charges are positive. I mean, not all the charges, you've got protons that are positive and neutrons that are neutral. If the electric force or the Coulomb force is so mighty, then how come atoms are exist and then nuclei inside the atom, they which are protons and neutrons exist? Well, it's because there is another type of force that is the strong force that it doesn't act very far, it just acts inside the nucleus and it will overcome the electric force. And in case of radioactivity, we've got the weak force, so we've got 4 types of forces. But as far as calculations are concerned, I'm just going to see how you calculate gravitational forces and how you calculate electric forces. And I really want you to appreciate that the electric force is mightier than the gravitational force. As a reminder here, Fg is G times m1 times m2 over d squared, and F electric is K times Q1 times Q2 over d squared. You see that G is 6.6710 to the negative 11, while K is 9 times 10 to the power of 9. And you see, and therefore, because of the difference here, this is 10 to the power of 9 and this is 10 to the power of negative 11, you see that Fe will beat Fg. Also, we have seen that the G, which is 9.8 or 9.81, is nothing but the G here times the mass of the Earth divided by Re squared. And be sure that to put Re in meters. Do not make that mistake leaving it in kilometers. Okay, I believe that's it.